I should share the screen if we're recording it, because otherwise whoever watches this can't see.
Oh, yeah.
Okay, so we're on the Jamboard doing problem 4 from calories. And when Caroline walks, 60% of the calories she burns are fat calories because of her age and other factors. How many fat calories did she burn from her 30 minutes of walking to and from the grocery store? So her total calories burned, we have to multiply those three things together. We need her weight, which means we have to go back here and go down to the amount for her, 120 pounds. So we'll plug that in. I think the 30 minutes is both going to and from, not each way. So maybe the answer key is going to disagree and I'm doing this a bad way, but I think that's what the problem is asking. And then the walking, move this out of the way, walking here, so 0.37 is what we use. That's calories per pound per minute. You don't have to label everything, but it's a good habit to get into. Okay, now it's the calculator's turn. 120 times 30 times 0.037. They get 133.2. We don't normally talk about tenths of a calorie, but I'm not going to round yet just because I'm still in the middle of my problem. And it's a good habit to not round until you get to the end. Then I'm going to say the next part of this is the 60%. So I'm going to have to take that 133.2, multiply it by 60%. And if you're still rusty with Riplop, then you can think up to yourself 60%. We'll go left out of percent. So we're scooting to the left and getting 0.6. Oops. And I'm getting about 80. I should use squiggly equals to show I'm rounding. These are just the fat calories. Okay, questions about that? No? Okay, I will stop the recording. For problems 5 and 6, Caroline is drinking milk. There's a bunch of red herring information that's here to distract us. So in the first problem, all we really need is that there's 5 grams of fat per serving, per cup, and she drinks 3 cups. All the rest about the carbs and the protein and the sugar, we don't need. That's only there to distract us. So we'll have each cup what do we multiply by for fat, 9 or 4?
9.
For the part 6, we're going to use part divided by whole. That's how we get the percent of an amount. So how much is 135 as a part divided by, oh, it's not telling us how many calories. So let's back up. We actually don't need that. Our whole is going to be 59 grams of fat. So if that's the whole, we also want to measure the part in grams. So we're just going to take this 5 grams here and say for those 3 cups, we're going to get 15. Everyone okay with my 15, even though I did it all out loud and not writing it down? We don't actually need the calorie amount. Okay, so 15 divided by 59, I get 0.254. And I'm rounding, so I'll make those wiggly. And then we'll say that's about 25%. Here I'm going to go into percent. So I'm going to the right into percent. Okay, third little review thing. We're going to talk about terms, which is in the mad science topic with order and terms. And this is something that is always a good review thing in Math 25. It's a part of Math 20 that is almost always either rusty or through no fault of your own, old teachers just didn't teach you this thing. So we're going to talk about this because it relates to what we are doing with the formulas of Math 25. Okay, many math students are taught to memorize PEMDAS. Raise your hand if you've seen PEMDAS. So if you haven't, that's okay. It's an acronym to help you memorize which has priority when you see a bunch of things. So P is parentheses, E is exponents, M is multiplication, D is division, A is addition, and S is subtraction. And if it's taught the right way, it's helpful, but if it's taught poorly, it isn't. So let's do this one with 8 divided by 4 times 2. So 2 students are arguing about which order to do this. One of them says, if I look at PEMDAS, then M comes before D. So let's multiply first and turn this into 8 divided by 8. And then 8 divided by 8 is 1. And the other student says, no, there's something I remember about going from left to right. So let's do the 8 divided by 4 first. 8 divided by 4 is 2. And then 2 times 2 is 4. So we get different answers. Which of these is the right way to do it?
Oh, are you asking us?
Yeah, I'm asking.
Let's see. We would have the factor of 4 times 2 and then divided by 8. Is that what you were asking?
Yeah, well, just top or bottom. Should we do it the top one where we prioritize the 4 times 2, or the bottom one where we prioritize the 8 divided by 4? Because we'll
yes, the bottom one.
Bottom one is correct. Yeah. So you have to know how this works. So hopefully someone has taught you. Multiplication and division have equal priority. If that's all that's left, you go left to right. And addition and subtraction have equal priority. If that's what there is left, go left to right. It's also true that PEMDAS doesn't tell us what to do with fractions. Anything you write as a fraction, I could take the fraction bar and replace it with a division symbol. Fractions are just sort of like division waiting to happen. And if I had something a little complicated on the top or the bottom, I would just toss it in parentheses to say that that's one thing. So if we really wanted to fix PEMDAS, which no one does, so no one ever writes this, but kind of think about it in your head. First, we have the parentheses and fractions bars. That comes first. Then we have any exponent stuff happen. Then we have our multiplication and division happen. And then we have our addition and subtraction happen. And at this point, I'm hoping you're saying, yeah, that makes sense. When this was taught to me, my teacher did a good job. This is very familiar. If you haven't been taught about PEMDAS, that's okay. It's just sort of a trick to remember these things. And again, hopefully even without the PEMDAS, it makes sense to you because you've been taught correctly before. But sometimes this is just still not quite enough. So we're going to talk about terms. So a term is when something is separated from the equal sign only by addition and subtraction. So here's 3 of these things. We're not going to solve them yet. We'll do this later. But for now, I just want to break them up into terms. These are just kind of getting annoyingly big. Even if I understand PEMDAS correctly, this still doesn't necessarily look easy to do. So how would I simplify this one? Where would I start? There's just a lot going on. So my advice is to underline where the terms are. Where are things separated only with a plus or minus outside of a parentheses. So there's one term, and then we get to a plus. And there's another term. Because there's a plus there that keeps it separate from the other parts. In this problem, I'll go along, doodly doodly doo. Here's a minus that's not in a parentheses. I'll start the next term. It goes to here. There's a plus not in parentheses, and 5 is its own term. Okay, you chime in for the third one. How big is the first term?
Just 11 in the beginning.
Just 11, and then there's a plus. How about the next term?
Times 2.
8 times 2, and then there's a minus that's not in parentheses.
And then another 8. Yeah.
7.
And then to the negative, or to the
Yep, we have some subtraction there. And that's its own. Okay, everyone okay with just identifying where the terms start and stop? So the nice thing about terms is that each term is completely independent until we combine them. So we have taken a big problem and made it 2 smaller problems. I can say that I'm going to be adding things, and it doesn't matter, you know, this side and this side, this term and this term don't mix up until the very last step. So for the first term, now I can use PEMDAS in a more bite-sized way. I have a addition in parentheses, I have division, I know parentheses happen first, so 4 plus 2 is 6. 6 divided by 3 is 2. On this side, the exponent happens first. 2 times itself is 4. 8 times 4 is 32. I don't need a third row. And finally, when I'm all done, I can just do my addition 2 plus 32 is 34, and I get my answer. Let's go to the slightly harder one. Here we have a minus and a plus. And I don't know if I need 2 rows or 3 rows, but I can simplify each term by itself. The 5 just stays 5. It's already just a number. How about this one? Half times 4 times 5. What do I do here? Oh, by the way, let me shrink this a little if that helps your screen.
Uh, 4 times 5 times 0.5?
I could, yeah. Just because I'm lecturing and recording it, then since it's all multiplication, I'll go left to right. In this case, it turns out it doesn't matter, but half of 4 is 2, and 2 times 5 is 10. For this term, the exponent will become a 4. 9 minus 1 is 8, so 3 times 8 divided by 4. And then it's all multiplying and dividing, so again, I go left to right. 3 times 8 is 24. And then 24 divided by 4 is 6. Okay, this is still 5, that is still 10. All the terms just stay independent until finally at the end, we can add them all up. 10 minus 6 is 4, plus 5 more is 9. Questions about those two before we go on to the hard one? Okay. So we have a term. The 11 is just its own thing. The 8 times 2 is 16, and it'll just stay 16 step by step. I don't think we need 3 steps in this one. 14 divided by 7.
Seven.
No, 2.
Oh.
Okay, this one will need 2 steps. So 19 minus 4 is 15, and then 15 divided by 3 is going to be 5. And lastly, 3 times itself is 9. Whoops, 9d. So 90 divided by 9 is going to be 10. So each term is its own thing, independent of the others. And then at the very end, we add everything up with pluses and minuses. So 11 plus 16 is 27 minus 2 is 25, plus 5 is 30, minus 10 is 20. So if I did my mental math correctly, there we go. So this isn't a kind of problem you'll have to do in Math 25. And even if you did, we're allowed to use calculators on everything in our class. So you could just plug all this into the calculator and it could do it for you. This matters because when we go back to the, oops. Come on, there we go. The health decisions and look at the metabolism formulas, then we have terms here. Each of these things that's written in parentheses, and we talked last class about you don't need the parentheses in your calculator. Your calculator is going to prioritize multiplying over addition anyway. but each of these is its own term. And we are seeing that in real life, we get these long expressions with terms because of different things happening. Whether it was in our homework problem that we did a little bit ago, where if we wanted to make a total calories formula, then each of these things we measure, how many carbs, how many proteins, how many fats, those are three terms that are added up at the end together. So this is just kind of a good lesson. What happens in real life when you have different sources of what you measure, then they become terms in an equation. When you have different sources of things you measure, whoops, then they become the terms of the equation. Okay, I'll pause the recording. So good review. We sort of started a little before the 2:30 class time and just kept going with different kinds of things. Now we're moving on to new material for Friday of week 2 with the food preparation topic. Okay. So as a lot of words, I'm not going to read them all. Go back and look at this after class. But the idea is that when you're in a commercial kitchen, then you have to be more careful in real life, in just your own personal kitchen. In my personal kitchen, if I just have a bunch of carrots, I can figure out some recipe that uses a bunch of carrots and good enough. If I have a little too few or too many, then that's okay. But if I'm scaling a recipe and I need to feed 200 people, then I better get this right. Otherwise, something bad's going to happen. And if you are in Math 25, some of you are in the culinary program in most terms. I haven't actually asked that for this crowd. So maybe at the end of class, I'll stop a little early, stop the recording, and we can all just talk about why we're in Math 25. But if you're in the culinary program, then the idea of making a meal for 200 people is something you've thought about a lot. If you're in Math 25 for a different reason, then this is something that will take some getting used to. We're going to do more review that we have a ratio, a proportion that a ratio is when we are comparing things like how much sugar per serving. And a proportion is the equation that has ratio equals ratio. And we see these all the time in real life. Let me just give you a quick example. If I'm driving 60 miles in 1 hour on the freeway, then how many miles would I drive in 90 minutes? Which I could say is 1.5 hours, something like that. So this is a ratio on each side, and the whole thing is a proportion. If I had anything else, like a +1 on this side, it wouldn't be a proportion anymore. The proportion has to be just ratio equals ratio. Everyone okay with my jargon review? Okay. So here are 4 problems on the screen, and I want to find out which ones are good proportions and which ones are broken proportions, because we want to make up lots of proportions. We want to read a word problem or think of a situation in the kitchen and write a proportion about it as we're scaling the recipes. And so we want to just quick and easy, always write a valid proportion and not a broken one. So let me grab this and put it on the whiteboard. Oops, that's not what I want. There we go. And I'm going to put it on the next slide also, because I know what's coming. Okay, so in the first one, Bill can drive 40 miles in an hour, and he can drive 80 miles in 2 hours. So people with 4 different colored pens have tried writing this out, which ones work and which ones don't.
Oh, the first one's the blue one.
The blue one. What about the blue one?
Oh, and the first one.
So you like the blue one? You think it works?
Yeah.
So they may use not highlight and smiley face. Okay, so blue one you like. Which other ones are good or bad for the 3 other options?
The first one?
The first one is good, yes. When you're deciding this, how are you deciding?
Because the same, like, values have to be, I don't know, like it can't be 40 miles over 80 miles because then that's not like, I don't know, it's not asking the same thing. But I'm not sure exactly how to explain it.
No, I see what you're saying. Yeah, the proportions way off if you don't arrange it correctly.
How do you know the green one is broken? Because you
Well,
are
if in 1 hour you can travel 80 miles, in 2 hours you would be doubling what the original 1 hour was. So it would actually, to equal 2 hours, if 1 hour was 80 miles, be 160 miles. So if you can travel, I mean, I guess if you're Superman, but
okay, let me give you some words. You're thinking good thoughts. So here's a little bit more about how to explain it. So we have 2 situations. In one situation, we have 40 miles in 1 hour. In another situation, we have 80 miles in 2 hours. In the equations that work, in the proportions that work, then you have to have something happen. So 40 miles in 1 hour, 80 miles in 2 hours. That's nice. See how it's symmetrical? And the blue one also works. 40 miles in 1 hour, 80 miles in 2 hours. That's symmetrical. In the ones that don't work, because if we hadn't figured it out yet, this one isn't going to work either, then it's not symmetrical. So we have 40 miles in 1 hour and 80 miles in 2 hours. Now one is going down and the other is going up. Or with the last one, 40 miles in 1 hour, 80 miles in 2 hours. Now we're crossing beams, which, like Ghostbusters, is bad. Another way to check this is that you often solve these by cross multiplying. 60 times 1.5 is 1 times y. Does that ring a bell? When I multiply in an X shape, my multiplications have to be equal. So is 40 times 2 the same as 80 times 1? Yes, they both equal 80. Is 40 times 2 the same as 80 times 1? Yes, they both equal 80. Is 40 times 80 the same as 1 times 2? Not at all. That's broken. Is 40 times 1 the same as 80 times 2? Not at all. That's broken. Make sense? So if we have a word problem and we want to turn it into a proportion, then we have 2 valid ways to do it. and this comes to how your personal brain works, almost everyone, like saying, we'll put a situation on the left and the other situation on the right. That just looks better. A very few people like this one. Let's put one situation on the top and the other situation on the bottom. But those people are rare, and since it's my job to be as clear as possible to as many of you as possible, then I will always do it this way. One situation on the left of the equals, the other situation on the right. And if it says miles on top on one side, it has to say miles on top on the other. If it says hours on the bottom on one side, it has to say hours on the bottom on the other. Everything has to be symmetrical and match. Make sense? Okay, let's look at number 2. I can grade 12 tests in an hour. I can grade 36 tests in 3 hours. Which of these are good or bad?
I think we should do the game one.
Green is good.
Green is good.
And blue is good, I think.
Blue is good. Yes. So going back to this thing, then 12 tests in 1 hour, 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 36 tests in 3 hours, 36 tests in 3. Well, that's not good. They're going opposite directions. 36 in 3 does work, doesn't work, closing games. Everyone happy with this? Should we do another one? Yes, okay. I'm gonna move back to this slide just so it's not too crowded. Bulk brown rice costs $2.20 per pound, so 5 pounds costs 11. Okay, think about that. I'm gonna turn off my mic and be right. Apologies for the interruption. So number 3, which ones were good?
Red, right? And
Green.
green.
Red and green. Okay, let's check. So 220 per pound, 220 per pound, 220 per pound, 220 per pound, 220 per pound. I have to do things in the same order. This one is trying to trick you by reversing which comes first in the sentence, the money or the weight. But if we started with money, we have to start with money. So $11 for 5 pounds. 11 for 5, great. 11 for 5, backwards. 11 for 5, great. 11 for 5, no. Good job. Okay, so if you were in Math 20, we would do a lot of this, but we're going to go onward because now we get the point. We can scale recipes. Let's look at number 25. A recipe uses 1.5 cups of sugar for 12 servings. So I should write that. 1.5 cups goes with 12 servings. And at this point, I stop reading the math problem. I don't care what it says. I know that because I have a proportion, I have to have one situation here, and the other situation has to also have cups on the top and servings on the bottom. That's what we just learned with all those colors. So now I keep reading. Your restaurant wants to shop for 200 servings How many cups of sugar do you need? Everyone okay with setting this up? Later on, we'll get to problems that try and trick us. Instead of cups in the second part of the problem, it might ask for pints or something like that. And we would have to be aware and not put down a pints number when it needs a cups number so it matches. But for now, we're not being tricky yet. Okay, earlier we talked about cross multiplying, so that's how we solve these. I'm going to expect we don't need too much review because most math 25 students don't, but tell me if you do. On one side, we have y times 12. And on the other side, we have 15 times 200, or 1.5 times 200. And 1.5 times 200 is 300. And then how do I solve the equations with y times something is something else? We haven't done that yet this term.
Is this one after you cross multiply and then divide it?
Yeah, the opposite of times 12 is divided by 12. But if I do that to one side, to be fair, I have to do it to the other. So 300 divided by 12, and I get 25. This is a word problem, so let's go back and say, we're in cups. That's our answer. Okay, first, your questions about this example problem. Okay, now I will talk a whole lot because I know what questions you should have even if you don't. So first I want to point out that there's nothing special about setting it up the way I did. Somebody else could have read this and they could have written the proportion 12 servings on top and the 1.5 cups on the bottom. But if they did that, then they have to be consistent. And on the other side, put the same thing on top and the same thing on the bottom. Everyone happy with that? Usually we tend to write the first ratio in just the order it gives us the word. Cups comes first, so I'll put that on top. Servings comes later, so that ends up on the bottom. But there's nothing broken about doing it the other way if you're consistent. Also, I want to point out that we have superpowers. So, oops, get big.
I have a quick question about the wording of the story problem. Like you were saying, it needs to follow the order. Now, would it be a trick question asking if it uses 1.5 cups of sugar for 12 servings, how many cups of sugar would you use if you want 200 servings? Now, would that be when they're trying to trick you up on the order?
They could phrase it differently. We'll see some trickier wordings later. So I'll just postpone that for now rather than try and make this one tricky on its own. Okay, my next comment is that when I have my cross multiplying, then doesn't matter which goes on the left and which goes on the right of my equal sign. No votes, yes or no? Okay, I'll just.
No,
leave
it doesn't really, I mean,
No.
wouldn't matter which side you start on.
Right, it's an equal sign. So anything here is the same as anything here. It doesn't matter which is which. So we have the power to pick, do we want to do this diagonal first or that diagonal first? We can pick any one we want to write on that side. Okay, also, if I'm multiplying 1.5 and 200, does it matter which one I write on the left or the right on its side of the equation?
I don't know.
No, you can, when you multiply two things, the order doesn't matter. Right? 4 times 8 is the same as 8 times 4, and so on. So we're going to combine those. And the way that my brain works as a math person, I really like it when my formula starts out with the letter doing stuff. So I am going to always pick the diagonal that has the letter to go on the left-hand side. And of those two things, I'm always going to pick the letter to write first. The other side, I don't really care which number I write first. You don't have to do this. You could put what's in blue on this side. You could put what's in green on that side. But just because of my math habits, I always like starting with the letter. And we do have the flexibility to do that. You can always pick this diagonal with the letter to be on the left side, and we can always pick to start with the letter. Okay, now let's do more of them and see if they get trickier. A recipe uses 30 ounces of canned pumpkin for 8 servings. Your restaurant wants to shop for 350 servings. How many ounces should be on the shopping list? So what do I write first?
Can you do x over 30?
I don't get
equals-
how many till much later on.
Oh, I see.
I'm going to avoid using my letter yet.
Okay.
I'll just start reading. A recipe uses 30 ounces. That's part of situation number 1 of canned pumpkin for 8 servings. So that's the other thing that goes together. That's my first rate. Everyone okay with that part? Then I stop reading. I finish making like the skeleton of my proportion. If I picked ounces on top, it has to stay on top. If I pick servings on the bottom, they have to go on the bottom. Okay, I'm done with my intermission. I keep reading. The restaurant wants to shop for 350 servings. So how many ounces of canned pumpkin do I need? okay with my setup part?
Looks good.
Oh. Then on one side, I have y times 8. Pick the diagonal with the y, and I put the y first. On the other side, I have the 350 times 30. Doesn't matter which order I do things.
That's a lot of ounces.
That is, yes, in real life, you wouldn't buy this by the ounce. So 10,500.
500, yeah.
We'll get to converting things to make it more realistic shopping lists later on. Pretty soon, but maybe not today because of how time is going. So divided by 8 gives me 1,312. I'll round up.
This is really interesting seeing this put out like this. Part of some of my job sometimes is we put together food boxes out of bulk food from, Cisco and American Food Products. And I don't know, it's funny seeing it on the Jamboard here because I mean that's almost exactly what we do on a regular basis when we do that.
Okay, I'm going to not move forward with the Math 25 right now, but I am going to do another talking just about kind of review stuff with this. There is a shortcut that you may have been taught about how to do these. And that shortcut says, first you have to set up your equation. You can't skip that part. So we have 30 ounces and 8 servings. And then we have, I don't know how many ounces, and 350 servings. The shortcut says there will be one diagonal that doesn't have the letter in it. Let me actually make that look like a diagonal. I'm not. Come on, why isn't it drawing? My pen stuck. It's very strange. Draw that works. Oh, this will be a challenge if I can't draw. Oh, I will try with my mouse. Um, that part's working. It's just, I'm going to close my Jamboard and reopen it because I can't do this well if I can't draw. Let's see if it will let me draw. That's bizarre. Oh, it's just not letting me hold down the mouse. That's working. Okay, one moment. There's more wording. Okay, so I was telling you about the shortcut. So the shortcut says that you start with the diagonal that doesn't have the letter, and for that diagonal, you multiply. And then there's some other number that's opposite the letter, and for that, you divide. Does that ring a bell to anybody?
Yeah.
So according to this shortcut, I can just say that y is going to be the 30 times the 350 divided by 8. And as we see from the previous slide, that's what we did. 30 times 350 divided by 8. And we'll get the 1313. Okay, so if you are ending your LCC math career in Math 25, this is a great shortcut. It will not trip you up. It saves you some steps. Everything is good. If you are going on to other math classes, Math 60 and higher, then don't do this shortcut. And the reason is, if things got a little bit more complicated, then this shortcut is a commitment. Let me show you what I mean by that. If I have y over 10 equals, let's say 2 over 5. Okay, can you just stare at this one and tell me what y is going to be?
It's gonna be a fraction.
No, it's a whole number.
Is it?
Is it?
Isn't four?
It is 4. So you could have done the shortcut I just said. The diagonal without the y is 20. Divide by 5. 20 divided by 5 is 4. You could also have seen that, wait a minute, going from this side to this side, this is a times 2 to get from 5 to 10. So we have to do a times 2 to get from 2 to 4.
I've seen that.
Okay, but now that we have an easy one to look at, what I taught you with the not shortcut way is we do our cross multiplying. We get y times 5 equals 2 times 10, right? So far, so good. And then it goes from there. What would happen if we were in Math 60 and instead of a y, this is a y plus 1? And if you haven't done Math 60, this might lose you, but that's okay. I'm just warning you about something that you don't care about. So in this case, now we have y plus 1 as its own thing, and we're multiplying by 5. And on the other side, we have 2 times 10, which is going to be 20. And I can proceed in 2 ways. I can do what's called distributing and take this times 5 and apply it to each part in the parentheses separately and get y times 5 plus 5 is 20. And I could keep going from there. Or I can say, no, I don't want to do that. Let's do a divided by 5 on both sides. And then this side has only the y plus 1 on it. And this side has 20 divided by 5 is 4. So there's 2 ways to proceed from here. Does that make sense? And the shortcut always picks one of them. It's the one that we have on the board at the moment, where first you multiply these and then you divide by the other part. And that's not always the fastest way to do these kinds of problems in Math 60. You are locking yourself to one path, whereas the other path might be a lot easier. So if you're going on to Math 60, it's important to always write out your multiplication step so that you can look at it and say, what should I do here? Because I have options. But in Math 25, we don't care. We're never going to have a +1 up here. It's just a very simple proportion. And if you like the shortcut, use the shortcut. It will never mess you up. Okay, that's really all I do have to say about proportions. Okay, where were we? Recipe scaling. So we've done our recipe scaling. The example problems we did had unrealistic answers. 25 cups of sugar. That's not right, because if you were actually in a professional kitchen, you would measure sugar in pounds, not cups. Cups are slow, scales are faster. And then 1,313 ounces of pumpkin is unrealistic because you would talk about pounds of pumpkins, not ounces. So let's talk about these conversion rates. We have 16 ounces is a pound. The Roman Empire used weights from which we get the words pounds and ounces. And an ounce saw various definitions across Europe. Usually it was either 450 or 480 grains of barley corn. That's a kind of small seed that's very uniform. If you put a big pile together, your pile and my pile are going to weigh pretty much the same amount because these seeds are so small. The Roman pound was 12 ounces. And the problem with 12 is it doesn't work well on a balance scale. If I am using a balance scale as a merchant, I want to be able to say, here's a big bunch of stuff. I put half on the left side of my balance, and I put half on the right side of my balance. And then again, if I want to get quarters, I would set aside one half, and of the other half, split it in half, and make those balance and have quarters. And if I wanted to split up my quarters, I'd get eighths. And if I wanted to split up my eighths, I'd get sixteenths. So that's what works well with a balance scale. So shortly after the Roman Empire ended, everyone said a 12 ounce pound was stupid. We can't do that on our scale. Let's use 16 because that's what our scales can make. So now we have 16 ounces in a pound because that's what works for balance scales. So here's a problem. Convert 1,313 ounces into a pound. And we know that 16 ounces is a pound. So this is exactly the same as before. We have two situations. One of them is 16 ounces is a pound. I stop thinking about the problem. I know that on the other side, ounces has to be on top and pounds has to be on the bottom. And now I look at what the actual thing is. I have 1,313. I want to figure out pounds. I can use that shortcut. I will take the 1,313 times 1 and then divided by 16. And I get about 82. And at this point, you might be thinking, that was way too much work. I can just look at this and know I'm supposed to divide by 16. And some people can. If you work with weights and measurement conversion and things like that a lot, then you get a good intuition. And is this a multiply by 16 problem? Or is this a divide by 16 problem? If you have that intuition, then you don't need to do as much work as we did on the slide. But if you don't have that intuition, or if you're the kind of person whose brain freezes up on a math test, then realize that this took away all the uncertainty. It told me when to multiply and when to divide, so I really can't mess up. So this is a nice, surefire, always works. I don't have to make any choices. I'm using that thing we did before where on one side I have one situation, On the other side, I have the other situation, and my physical arrangement of the numbers on the page means I will always get the right answer. I don't have to worry about should I divide or should I multiply. So yay, things that you can't mess up even if your brain freezes on a test. But if this is too much work on homework, you could just look at this and say, I'm dividing by 16, then go ahead and be quick on the homework. That's fine. You could even be quick on the test if you're up. Okay, parts of a gallon. We have 8 fluid ounces is a cup, 2 cups is a pint, 2 pints is a quart, 4 quarts is a gallon. If you have trouble remembering that, then here's a picture. Here's our gallon. We chop it up into fourths and get quarts. That's why they're called quarts, because they're quarters. Each of those we chop up and we get pints. And then the pints, we chop them up and we get cups. Again, we have 16 cups in the gallon, just like 16 ounces in the pound. Merchants like chopping things in two because that's what you can do with a balance scale. We can combine it all into one picture. So if you're someone that wants to have nice, efficient notes, then this picture here is a good one to put in your notes about the parts of a gallon if you don't use them enough to have it memorized.
I like those little charts, actually, a lot.
And finally, why do we say mind your P's and Q's? If we were in an old English pub, we didn't want to burn through all the firewood in our houses, so we'd go to the pub every night in winter to stay warm together, and then go home and sleep under blankets when we really wanted to. Then we would drink, and we might only get paid once a month. So there would be on the wall behind the bartender would go P and Q to mark pints and quarts for how much we're drinking. And then we'd pay up when payday happened. So mind your P's and Q's meant don't drink too much before payday. Even though these days we only tend to say mind your P's and Q's to kids, hopefully for other reasons. Side note, we're in the grass seed capital of the world. There is something called a dry quart. If your family is in the grass seed business, you know what that is. Don't talk about it. It will confuse people. Okay, let's do this other problem. Convert 30 quarts into cups. So, okay, again, if you are someone used to working with quarts and cups, you can just look at this and know, should I divide by 4 or should I multiply by 4? But we are not assuming you are that kind of person. So we'll do it the slightly longer way. So I want quarts and cups. So in general, how many cups are in 1 quart? Look at the picture. 1 quart is 4 cups. Take an intermission. The other side has to have cups on the top and quarts on the bottom. Look at my other situation. Situation 2 says I have 30 quarts. How many cups? Do you want me to use the shortcut or multiply and do all the steps?
You could multiply.
Multiply. Okay, so going back to review how that works, pick the diagonal with the y. Y times 1 is just y. Take the other diagonal, 30 times 4. By the way, if you don't like y's, you can use other letters. I just don't like x's because they look like times symbols. Ta-da. Okay, we have only a minute, so we'll just do a little more. We have measuring spoons. 3 teaspoons is a tablespoon. 16 tablespoons is a cup. And if I take this one and divide it by 4 on both sides, I get that 4 tablespoons is a quarter cup, which seems a little awkward, but you actually use this a lot when baking at home in the kitchen.
Oh,
That if I have something with a quarter, something in cups, and I want to take like a half recipe, then what's half of a quarter cup? It would be 2 of the tablespoons. So as always, Math 25, everything is open calculator, everything is open notes. So one of your jobs, maybe soon, this weekend, is to take all these measurement conversions and the ones you don't already know, put them somewhere convenient. Okay, so we can do lots more of these kinds of things when you see me again. Any other questions before we're done? Let me stop sharing. I just got a few emails and stop recording.